Yeah. Okay, here for NMOS enhancement mode transistor like this, and PMOS depletion mode transistor, okay, like this. In the here, what is the difference between enhancement mode and depletion is, in the depletion mode transistor already channel is present. Okay, that is here representing. Okay, your implant is there. Okay, your implant is there. That is called that is we call it as a channel. Okay, here channel is already exist in the depletion mode transistor, but whereas in the enhancement mode transistor, okay, channel is not present. Okay, when we apply gate to source voltage greater than threshold voltage, okay, then only the channel is enhanced, means the channel is formed, okay, near the oxide layer. Here near the oxide layer channel is formed. Okay, when these conditions are satisfied, means VGS greater than threshold voltage and drain to source voltage greater than VGS minus VT, then these three conditions are there. When these three conditions are satisfied, okay, then only the current will flow in the drain, output drain current, ID. Okay, here this is for PMOS enhancement mode, same, okay, as per the NMOS. Here for three here MOSFET operates, okay, three region of operations. One is cutoff mode, next one is linear or ohmic, next one is saturation. Okay, based on the three conditions, okay, here you can see the transistor. Here when VGS greater than VT, okay, here threshold voltage, when gate to source voltage greater than threshold voltage, device is on, but VDS is 0, okay, there is no current to flow, because here VDS also should be less than or greater than VGS minus VT. Here it should satisfy these two conditions, this one and this one. Okay, then only the current will flow in the output, that is drain current. Here just device is on, okay, very small amount of current will flow, okay, that is negligible. But when VGS greater than VT, VGS greater than VT and uh, VDS less than VGS minus VT, that is linear region or ohmic region. Here current, okay, linearly increases like this. Okay, and linearly increases for different gate to source voltages, different gate to source voltages. When again here VDS greater than VGS minus VT, here we will get current constant. We get current constant. Okay, that is called saturation region. Okay, when we keep on increasing this VDS drain to source voltage, okay, because of this uh, drain volt drain voltage potential, here depletion layer is increases, here depletion layer is increases, then channel is pinched up, means here channel is closed. Okay, this white region is called the depletion region. This white region is called depletion region. When we keep on increasing this drain to source voltage VDS, okay, at particular voltage channel is pinched off, means uh, here channel is blocked, and at particular okay voltage you will get constant current. Okay, this region is called constant current source, or we can call this device as a acting as a constant current source. Okay, this is for uh, okay enhancement mode transistor. Your channel is already present, so this is called a depletion mode transistor. So now we will see the uh, NMOS fabrication. Okay, NMOS transistor fabrication process steps we will see. Okay, in the NMOS transistor we will take p-type substrate. Yeah, if you see here, okay, NMOS transistor, okay, this is p-type substrate. This is p-type substrate. Okay, suppose if you want PMOS device, okay, we'll use n-type substrate. Okay, like that. Here first, if you see first step, okay, we'll take wafer, that is, okay, we will take p-type substrate, that is called wafer. Okay, here processing is carried out on a thin wafer cut from a single crystal of silicon of high purity, into which the required impurities, here p-type, okay, semiconductor, so we will take p-type impurities are introduced as the crystal. Okay, whenever this semiconductor is growing, okay, we will apply p-type impurities to get the p-type semiconductor. Okay, that is called it as a wafer, or we can call it as a p-type substrate. Okay, here just indicating the p-type substrate notations, just symbol here. These are the okay p-type substrate notation symbols, and then okay onto which substrate, okay, a layer of silicon dioxide or SiO2 layer, okay, thick oxide, we call it as a thick oxide here. Okay, layer of silicon dioxide SiO2, typically it is 1 micrometer or 1 micron thick, is grown all over the surface of the vapor to protect the surface. Okay, for any breakage and to protection, you will use this thick oxide layer. Okay, it acts as a barrier to dopants during processing and provide a generally insulating substrate onto which other layers may be deposited on pattern. Okay, uh, on which this silicon vapor, this silicon dioxide layer or insulating layer, we can start the process. Okay, next we will deposit photoresist. Here, after thick oxide or silicon dioxide layer, we will deposit photoresist layer in the third step. Okay, the surface is now covered with a photoresist which is deposited onto the wafer and spin coating. Here, photoresist is a uh, polymerized material. Okay, there are mainly two types of photoresistors there: positive photoresist, negative photoresist. Okay, this is a polymerized material. Okay, we will see the use of photoresist later. Okay, in the third step, after photoresisting upon the silicon dioxide. Okay, this photoresist is applied by using the spin coating technique. Means when we pour this photoresist on the silicon dioxide, we will put in the spin coater. Okay, that we will put that vapor in the spin coater device. That spin coater will okay will spun some particular speed, so that the this photoresist layer is okay even distribution of the required thickness. Okay, we will get the even thickness for the entire wafer. Next, after photoresist, okay, now we will apply UV light, ultraviolet light. The photoresist layer is then exposed to ultraviolet light through a mask which defines those regions into which diffusion is to take place. Okay, here if you see here, okay, applying UV light here. Okay, this is the mask. Okay, after photoresist, this one we will apply UV light. Okay, here mask is there. Here mask is there. Here not there. Means in this area we will allow this UV light to pass it into the wafer. Remaining areas, okay, we are not allowing this UV light. Remaining areas we are not allowing this UV light. Only particular this area we will allow UV light. So after this UV light okay, applied, then we will put it, this vapor in the development. Okay, we will apply development. In the development section, okay, this photoresist and here this silicon dioxide layer will be removed. Okay, here silicon dioxide layer will be removed only this particular area region. Okay, remaining positions is as it is. Only the UV light allowed area will be removed. Okay, remaining portion will be same. Okay, these are all fixed. Okay, this area is removed. Okay, after development. Okay, here development is done by the etching process. Means here photoresist is etched away and this particular okay silicon dioxide layer also etched away. Okay, then we will get like this structure. Okay, this is like a we can call it as a window in oxide, like this. There we will grow gate. Okay, there we will grow gate. Okay, before growing this okay gate structure, then here we will apply okay patterned poly. Okay, then here we will apply thin oxide. Okay, this is called thin oxide. Okay, we will apply thin oxide. After thin oxide is formed, again we will use same, we will apply UV light. Okay, we will apply UV light. Okay, so that this portion will be removed. We will see in the next slide. Here. Okay. Okay. This region is called the thin oxide. Okay. After thin oxide, we will apply gate material, that is, okay, this is called polysilicon. For the gate terminal, we will deposit polysilicon, okay, material over this entire surface. Okay, we will apply over this entire surface. Then okay, we will apply this same procedure. We will apply UV light, okay, and this only here this polysilicon will be present, remaining area will be removed. Here only this polysilicon will be present, remaining material will be etched away. Okay, after forming this polysilicon, okay, next we have to, okay, diffuse the source and drain. Here we have to use source and drain diffusion. Okay, for that purpose, uh, here we are using the p-type substrate. This is p-type substrate. Now here diffusions are n plus diffusion. Here n plus diffusion. Okay, here thin oxide layer will be removed. Again, for this process also, some of the steps may be repeated. Here total steps are not included, but some of the steps are repeated. Means, okay, depositing thin oxide layer, then uh, okay, applying the photoresist, then UV light. Okay, this particular area will be opened. Then okay, here again you will apply here some layer, or SiO2 layer we can apply here. Then we will diffuse the n plus semiconductor. Okay, this diffusion will be uh, done using the diffusion is achieved by heating the vapor to a high temperature and passing a gas, okay, containing the desired n-type impurity material. Okay, or here for example n-type material is phosphorus over this surface. So at high temperature, this n plus diffusion or phosphorus uh, here impurity ions will be diffused into the this area. Okay, this area. So based on the time, the thickness and width of the this diffusions, okay, will be formed. Okay, how much thickness we want and how much depth we want, okay, based on the time and concentration of the, okay, uh, temperature, okay, this diffusion can be formed. Okay, after the forming this okay, diffusions here, n plus diffusions means, okay, this is for source and this is for drain. Okay, after forming this one, contact holes means we need to connect external terminal. Okay, you need to connect external terminal. So this is for source Okay, this is gate, this is drain. So for the external terminal connection, okay, we will form the cuts, contact holes. Here if you see, this is for source, gate, drain. So forming the insulation between the gate, source and drain. Okay, here forming the again this layer. Okay, insulation layer, dielectric layer here and here. Okay, here also. Okay, if you see here gate this side, okay, this side, and here drain, source, these two sides. Okay, after forming these cuts, contact holes, okay, we will use metallization. Okay, pattern metallization. Okay, naturally we will use aluminum. Okay, thickness is 1 micron. Okay, we will apply here metal, here metal. This is for source and this is for gate, this is for drain. Okay, drain, gate, source. Okay, like this we can, okay, form this NMOS transistor. And whereas for PMOS structure, okay, procedure is same, but here we will use substrate as a N-type substrate. Here diffusions are P plus diffusions. Procedure is same, but the diffusion is P plus diffusion. Okay, we will use boron or some P-type semiconductors. Okay, we can use. And PMOS, their mask may be different. Okay, here mask will be different. Here this mask, whereas P type we will use different mask. Okay, uh, okay, some of the steps may be repeated in the CMOS also, CMOS by CMOS also. Here some of the steps may be repeated and some of the steps may be added. Okay, some steps are added, okay, based on the technology by CMOS or by CMOS technology. Okay, we will use. Okay, this whole thing will be available in the textbook Essentials of VLSI Circuits and Systems book. Okay, next class we will see NWEL process. Okay, CMOS, PWEL and NMOS process we will see in the next class. Any doubts? Uh, okay, now time is getting out. Okay, next class we will see the PWEL, CMOS PWEL process. Okay, I will close this meeting. Okay.